Hello everyone, my name is José Roberto, and in this presentation I will show you the results obtained in the last years about point defects in hexagonal boron nitride. In particular, I will talk about point defects produced by neutron radiation, and I hope that I can show you the promised applications that can emerge, principally to quantum information science from this defect engineering. Um, Here, this is my email, so if you want, you can send a message to me, and let me turn off my camera, and we will begin with this presentation. Well, here we have a brief overview about some properties of hexagonal boron nitride. This material is formed stacking these hexagonal layers of boron and nitrogen, and this stack direction defines this z-axis direction. These layers are held together by van der Waals interactions here, and these make possible to exfoliate the material layers. Its great band gap of approximately 6 electron volts uh, makes it relatively easy to produce isolated defects in the material, which makes possible that you promote internal transitions between the energy levels of a defect. Possibly this is the most important optical feature of the hexagonal boron nitride involving point defects. The discovery of single photon emission at room temperature has given HBM the status of promising material for applications in quantum information technology. This type of emission is characterized by a sharp luminescent band which emits photons in a constant time interval. Here we have some works uh, that observe this type of emission, and here we can see these sharp lines around a well-defined wavelength emission. Most important here is the fact that these emissions are from intrinsic point defects in the material. So we can raise some questions. Uh, what is the microscopic structure of the defect uh, who emits the single photons? How can I produce them? And do all defects in the material have single photon emission? So these are the objectives of this work. Produce defects in hexagonal boron nitride using neutron irradiation, study the produced defects using electron paramagnetic resonance, and determine its thermostability by annealing experiments. The neutron radiation makes possible that defects can be produced in a controlled way. The concentration of the defects is proportional to the radiation dose. In addition, particle radiation is more likely to produce vacancy-type defects, which gives us greater control over the types of defects produced. 3 samples were used in this work. 2 of them are powdered samples. One of them is a flake from 2D semiconductors, and another sample is ultrafine grains commercialized by Graphene Supermarket. Both samples are very similar in EPR measurements. And the third sample is a crystal, here, a little crystal, but this crystal has a problem. Only its Z direction is well defined. Its hexagonal layers of boron and nitrogen are well stacked, but they are twisted randomly around this stacked direction, which gives this distorted representation of the reciprocal lattice site of the material. The use of neutron radiation to produce point defects in hexagonal boron nitride is already known. In our previous work, this PRV here, we provide the first description of a high-spin center produced in powder rate samples. This center is responsible by the peak color gain, here in this figure for example, in the samples after radiation, and by optical absorption measurements, here in this figure, we observed a broad absorption band covering almost all the visible region, with a maximal absorption around the green spectrum region, here. The EPR spectrum of the center is well described considering a spin-1 system with zero-field splitting of approximately 3.66 GHz. Here the parameters, here we can see its EPR spectrum composed by these three lines. The EPR spectrum of the center is well described considering a spin-1 system with zero-field splitting of approximately 3.6 GHz, a G factor E2, and it is thermostable up to 600 degrees Celsius of exposure. Another research group also using EPR measurements determines that this high-spin center is associated with a boron vacancy in a negative charge state. Note that its EPR spectrum is very sensitive to green illumination. Confirm that this absorption band here in the visible region is in fact of the spin-1 defect. However, there are other EPR signals in neutron-irradiated HBN that need more explanation. In these three panels, here, here, and here, we have the EPR spectrum of HBN samples after neutron radiation. In the left panel, this one, is shown the EPR spectrum of the boron vacancy, whose spin Hamiltonian parameters is already known. In the other two panels, here and here, EPR data without a model to explain it. These centers, both of them has spin-1 half, and apparently the EPR spectra in powdered samples are more complex than that of crystalline sample. Let's begin with the EPR spectrum of the crystalline sample. It is formed by three lines here, when the magnetic field is applied along the C direction, and this line gets closer as the magnetic field moves away from the C axis. When the magnetic field is applied always parallel to the hexagonal layers, here in this figure, the EPR spectrum always exhibits a single line. This behavior in both cases is represented in this video here, where these EPR lines were simulated using these spin Hamiltonian parameters here in this table. An EPR spectrum may be composed by three lines when we have a hyperfine interaction here, a hyperfine interaction between an electronic spin 1/2 and a nuclear spin 1. In the case of hexagonal boron nitride, the nuclear spin may be associated with a nitrogen nucleus. Adjusting these line positions here in these two figures of the EPR spectrum here, and these positions are represented here by these black points, and the line positions here in this figure are represented by these black points. Adjusting these line positions, we obtained these spin Hamiltonian parameters using this equation here. And now we can describe how the electron and the nitrogen nuclei are interacting. The principal directions of G tensor and hyperfine tensor are along the C axis. In the plane of the samples, the parameters are more difficult to interpret due to polycrystalline character of the sample. And this difficult to interpret them may be one of the reasons that the three EPR lines lose resolution and the final EPR spectrum exhibit this single line. For annealing experiments, we heated the samples and after that measured its EPR spectrum. During the thermoannealing experiments, the three hyperfine lines here, labeled as D1, persists until approximately 550 degrees Celsius, and at this temperature, a second EPR signal can be clearly observed, and it is this single line here. This new signal will be labeled as D2. At this point, the sample also loses its pink color, which is the optical signature that the boron vacancy, the spin-worn center, also was annealed out. To understand this annealing data, spectral simulations were done to all EPR spectra in this figure, considering a spin system composed of two parts, the D1 and D2 signals, and the simulations are shown in these three figures here. As can be seen from the sum of the signals, here the D1 plus D2 in all cases, the simulated EPR spectra adjust very well on experimental data. These EPR simulations make clear that above 550 degrees Celsius, the signal D2 exhibits a much broader line width and the hyperfine signal D1 reappears. At room temperature, for example, the signal D2 is very weak and its line width is comparable to that of signal D1. After that, the signal D2 is much broader and intense, and the signal D1 reappears. So, the reappearing of the nitrogen hyperfine interaction accompanied by the broadening of signal D2 may be an indicative that both defects are transferring charge to each other, whereas the disappearance of the signal D1 along with the color of the material may indicate that the boron vacancy transfers charge to the defect D1 and both lose their paramagnetic state. So what we have about the D1 signal until this moment? 1. There is a hyperfine interaction involving a nitrogen nucleus and an electronic spin 1/2. 2. Its hyperfine principal component is aligned with the C-axis. And 3. It has a good thermal stability, persisting to thermal treatments until 550 degrees Celsius. So, theoretical predictions point that the pair defect VN&B, a nitrogen vacancy next to a nitrogen antisite, obey these conditions. In its neutron charged state, it's characterized by a spin 1/2, whose wave function is distributed in the pz orbital of the nitrogen antisite. Here, for example, this is illustrated. In agreement with the experimental data, it's predicted that this pz orbital is parallel to the c-axis direction. So, in agreement with the observed in the experiments and what is proposed by theory. The good thermal stability could be a consequence of the associated nitrogen vacancy of the defect, since that isolated vacancies are predicted to be stable even when exposed to high temperature. For example, here in this work, this PRB, there are several anneal temperature for several defects, and the vacancy type are the most stable. It is useful to remind that this pair defect, the VN&B, until this moment is pointed as the responsible for the single photon emission in 1.95 electron volts in HBN samples. So the EPR data present in this work could bring new insights on physical properties of this defect. Since the VNNB defect was produced by neutron radiation in HBN crystals, we tried to use it to explain the EPR data of powdered samples. However, considering only this defect here uh, was insufficient, as can be seen in these figures. Only the signal D1 does not reproduce the experimental data observed from samples. When the samples were heated at temperatures above 500 degrees, here 500 degrees, a structure composed by 5 lines is clearly observed in the spectra. So the model considering the signals D1 and D2 used for crystalline samples needed to be improved with a third signal called D3, here D3, to be possible generate the observed 5 lines. So the signal D3 is composed by 5 EPR lines necessary to explain the experimental data. The simplest way to implement this third signal was admitted that it is formed when two nitrogen nuclei are interacting with an electron. In an EPR experiment, this is described by a super hyperfine interaction that is illustrated by a spectrum formed by 5 lines showing an intensity ratio of 1:2:3:2:1. That is, the central line here, here, and here is 3 times more intense than the first and the last lines. The signal also has a good thermal stability, persisting to thermal treatments up to 900 degrees here. At this temperature, the EPR spectrum is very, very weak. Another interesting point that occurs in powdered samples is that the VNNB defect is permanently annihilated out after the thermal treatment at 550 degrees, and the signal D2 is more stable under thermal treatments in comparison to that of crystalline sample. In this case, it is not broadened after 500 degrees. Only its intensity slowly decreases until zero at approximately 900 degrees. It is possible with an extra point defect whose generated the signal D3 that the thermal level is shifted and then the VNNB energy level becomes more isolated into bandgap. To propose a point defect as responsible for the signal D3, two conditions can be imposed based on observed EPR experimental data. 1. The defect needs to be capable to show a super hyperfine interaction involving two nitrogen nuclei and an electronic spin on half to generate the 5 lines observed. 2. It is possible that a vacancy associated with its structure warrants that the defect has good thermal stability. A possible candidate who meets these conditions is the boron vacancy complex with carbon impurity on nitrogen site, this defect here, CNVB. By DFT calculations, it is predicted that this defect reaches a paramagnetic state with spin on half when an electron is donated or accepted by the defect. Once that the carbon isotope without nuclear spin is dominant, the nitrogen nuclei in the first vicinity of the boron vacancy, here nitrogen and this nitrogen nuclei, will give rise to the super hyperfine interaction necessary to generate the 5 lines observed in the EPR spectra. The necessity of the CNVB defect receive or donate an electron to reach the spin on half state can be used to explain why the EPR signal D2 in powdered samples is more stable than that in crystalline sample. Remember that the signal D2 in crystalline sample before the thermal treatments has low intensity and its line width is compared to that of signal D1 here. the signal D2 is weak and its line width is almost the same of D1. After the treatment at 550 degrees, its intensity and line width turns bigger, which was interpreted as a consequence of charge transferring between the signals D1 and D2. In the case of powdered samples, we will reuse this interpretation, but applied to the defect associated to the signal D2 and to the CNVB defect responsible for the signal D3. We can speculate that even at room temperature, the signal D2, the defect associated to signal D2 transfer a charge to the CNVB defect, so it reaches the spin 1/2 state. In this way, the signal D2, the unknown defect, suffers the line width broadening and the CNVB defect is now a spin 1/2 center. This model can be complemented with more information to confirm its validity. However, for this, the ideal is to repeat this investigation in high-quality carbon-doped HBN crystals, which makes possible to carry out EPR angular dependency measures that are much richer in information than EPR powder spectra. Finally, what we can present as general conclusions so far. 1. The neutron radiation produced 4-point defects in HBN, the negative boron vacancy with spin 1, with more 3 spin 1/2 defects, which are the VNNB defect, whose DFT models are in good agreement with the EPR experimental data. 2. The VBCN defect observed only in flake and ultrafine powdered samples. And 3. A third unknown defect, but based on thermoanneal experiments, plays an important role in the thermostability of the spin 1/2 defects in neutron-irradiated HBN. Another point important is that the good thermostability of all defects induced by neutron radiation make them promise in future optical applications, for example. And this work was just accepted for publication, and the accepted manuscript is available to be read on Journal of Physics D. So if you want, please check the publication or send me an email to discuss the work with more details. Here's my camera again. Hello. Well, I am very grateful that you attend to this presentation, and I hope that I was able to show you the good possibilities that can be explored both scientifically and technologically with the production of point defects in HBN. I would like to thank the organizing committee of this event for making it possible in a virtual environment, and the Brazilian agencies, CNPq, FAPEMIG, and CAPES, for making this work possible. So thanks so much.